Okay guys, so in this lecture we'll be starting off with the discussion on catalyst. So let's get started. So catalyst, it is a substance that increases the rate of reaction without itself being consumed during the course of reaction. So it is a substance that increases the rate of reaction increases the rate of reaction without itself being consumed. Okay, so another way of seeing the same thing is that if catalyst participate in a complex reaction, then it must be regenerated. If catalyst participate in a complex reaction, then it must regenerate. Okay, and a catalyst provides an alternate path with lower activation energy. Catalyst provides an alternative path with lower activation energy. Okay, and another point for a catalyst is a catalyst can affect A or EA or both, but in general we consider that um, only we see the change in activation energy, not in A. Okay, so a catalyst can affect A and EA, but or both, but in general we consider only change in activation energy. Only activation energy. Okay, so graphically if we want to represent this, then suppose we have a graph of, let's say, the potential energy with reaction coordinate, then we can say that initially if this was the graph taken by the reactant to convert itself into products, then this was the EA which was required, or the activation energy which was required. Now after the introduction of the catalyst, so this was the activation complex. First let me write down this. So this was the activation complex, this is the activation energy which is required, and this is the path without catalyst. Okay, now what will be the path in presence of catalyst? So this would be the path in presence of catalyst. We see a significant lowering of the activation energy which is required to convert the reactants into products. Okay, so this is EA dash. Okay, so this is the path in presence of catalyst. Presence of catalyst. Okay, and this is the final product. So we see that due to the presence of catalyst, the activation energy which was required gets significantly reduced. Okay, so let me put down this in words, that EA was the activation energy in absence of catalyst, in absence of catalyst, and EA dash is the activation energy in presence of catalyst. Okay, then we can again say that let's say we have ln k is equals to ln a minus e upon rt, and this is in absence of catalyst, and we have ln, this is, let's suppose, k here and this is k dash here. So in presence of catalyst it would be ln a minus ea dash upon rt. We are assuming we are doing the experiment with same temperature. So if we actually subtract first from 2, or rather anyhow if we subtract even 2 from first, rather first from 2, so we will be getting ln k dash minus ln k, which would be equals to ea upon rt minus ea dash upon rt. So we can write ln k dash upon k would be equals to ea minus ea dash upon rt. Okay, so from here we can calculate the ratio in which we get more activation, or rather more rate of reaction in presence of catalyst. So we can also have a negative catalyst which can actually increase the activation energy of the reaction. Suppose we have a graph of potential energy and reaction coordinate. Okay, so we can even have a graph something like this, in which a catalyst can actually increase the activation energy of the reaction. Okay, so this is a negative catalyst, okay, which actually increases activation energy. Okay, so next, for a reversible reaction we can say that as reactants gets converted into products, we have kf and kb for the rate constant, which are the rate constant for the forward and the backward direction. We can say that delta h or delta e would be equals to ea of forward direction minus ea of backward direction. Okay, so this is in absence of catalyst, and in presence of catalyst you can even write ea dash in forward direction minus ea dash in backward direction in presence of catalyst. So the graph would look something like this. Again, potential energy on the y-axis and reaction coordinate on the x-axis. Suppose we have this as the initial graph, and after the introduction of the catalyst we have this graph. Okay, so this was E A dash in forward direction, this was EA in forward direction. Similarly, this was EB, or rather EA in backward direction, and this was EA dash in backward direction. And these are products formation stage, and this is reactant. Okay, so the difference of energy in forward direction and the energy in backward direction would still remain the same in both the cases. Okay. Where EA is in, just for the documentation purpose I'm writing that EAF is the activation energy of forward direction and EB is the activation energy of backward direction. EAB is the activation energy of backward direction. Similarly, these are actually in absence of catalyst. Okay, if I write EA dash F and EA dash B, then it would be in presence of catalyst. Okay, EA dash F and EA dash B. Okay, so similarly I can also write, this is the equilibrium reaction, so we can write K equilibrium would be equals to KF upon KB. So the K equilibrium would still remain the same whether we are adding catalyst or not. Why is this the case? Because the catalyst would increase KF and KB in equal proportion, hence K equivalent would have no change. As both KF and KB would increase due to the presence of catalyst, the K equivalent would still remain the same even in presence of catalyst. So this is a very important point to keep in mind. Okay, so what all quantities or what all terms have no change even due to presence of catalyst? They would be, first, as we discussed, K equivalent, other not, let's not have a point. So K equivalent, delta H and delta E would also not be changing, or delta G, which is change in Gibbs energy. Okay, we will be discussing more on Gibbs energy in our coming video lectures. So these are all the terms which would have no impact even when we introduce catalyst in the reaction. So with this we come to the end of this lecture. In the next lecture we'll be continuing on seeing more on catalyst and the related graphs. So till then, good luck and goodbye.